Imagine looking into the night sky and realizing that some of the tiny pinpoints of light you see are not stars at all, not even galaxies in the ordinary sense, but something far more extreme. Quasars are among the most powerful and mysterious objects in the universe, releasing more energy than entire galaxies while occupying a region no larger than our solar system. The word quasar comes from quasi-stellar radio source, a name given in the mid-20th century when astronomers first detected them as strange radio-emitting points that looked like stars but behaved nothing like them. At first, no one truly understood what they were seeing. These objects were incredibly distant, unbelievably bright, and seemed to defy the known laws of astrophysics at the time. To understand quasars, it helps to first understand galaxies. A galaxy is a massive system of stars, gas, dust, and dark matter bound together by gravity. At the heart of almost every large galaxy lies a supermassive black hole, millions or even billions of times more massive than the Sun. Most of the time, these black holes are relatively quiet, hidden in the center of their galaxies, exerting their gravitational pull without announcing their presence dramatically. But when large amounts of matter fall toward a supermassive black hole, something extraordinary happens. The black hole itself does not shine, but the material around it does. This is where quasars are born. As gas, dust, and even stars spiral toward the black hole, they form a rotating structure called an accretion disk. Friction and gravitational forces within this disk heat the material to extreme temperatures, causing it to glow intensely across the electromagnetic spectrum, from radio waves to visible light, ultraviolet, and even X-rays. The energy released during this process is astonishing. A quasar can shine with the brightness of hundreds of billions of stars combined, making it visible across vast cosmic distances. In fact, quasars are so luminous that they can outshine their entire host galaxies, rendering the galaxies themselves almost invisible by comparison. One of the most remarkable things about quasars is their distance. Many quasars we observe today are billions of light years away, meaning their light has traveled for billions of years to reach us. When we look at a distant quasar, we are seeing it as it was when the universe was very young. Some quasars formed less than 1 billion years after the Big Bang, making them among the earliest known cosmic structures. This makes quasars incredibly valuable to astronomers because they act like cosmic lighthouses, illuminating the conditions of the early universe and helping scientists understand how galaxies and black holes evolved over time. In the early days of quasar research, their extreme distances were not immediately obvious. When astronomers first measured their spectra, they found strange patterns of emission lines that did not match any known elements. It was only later that scientists realized these lines were familiar elements, but shifted dramatically toward the red end of the spectrum. This phenomenon, known as redshift, occurs because the universe is expanding, stretching the light from distant objects to longer wavelengths. The enormous redshifts of quasars revealed that they were not nearby oddities, but objects located at the very edge of the observable universe. This realization fundamentally changed our understanding of the cosmos. Quasars are not just bright. They are also highly energetic and often violent. Many quasars produce powerful jets of charged particles that shoot out from the regions near the black hole at nearly the speed of light. These jets can extend for hundreds of thousands or even millions of light years, far beyond the boundaries of the host galaxy. As they plow through intergalactic space, they interact with surrounding gas, heating it, compressing it, and sometimes triggering or suppressing star formation. In this way, quasars do not merely exist within the universe. They actively shape it. Another fascinating aspect of quasars is how quickly their brightness can change. Some quasars vary in luminosity over days or even hours. This rapid variability tells scientists that the region producing the light must be relatively small, because changes cannot occur faster than light can travel across the emitting area. This observation provided strong evidence that quasars are powered by compact objects like black holes, rather than by more spread-out processes such as massive clusters of stars. The immense energy output combined with the small size of the source pointed directly to accretion onto supermassive black holes as the most plausible explanation. Despite their incredible power, quasars are not permanent features of galaxies. They represent a phase in a galaxy's life cycle. When a galaxy has abundant gas available to feed its central black hole, the black hole becomes active, and the galaxy can shine as a quasar. Over time, as the available fuel is consumed or blown away by energetic winds and radiation, the quasar fades. The black hole remains, but it enters a quieter state. This means that many galaxies we see today, including our own Milky Way, may have gone through a quasar phase in the distant past. The Milky Way's central black hole, known as Sagittarius A*, is relatively calm compared to the monsters that power quasars. It accretes matter slowly and emits modest amounts of energy. But evidence suggests that even Sagittarius A was more active millions of years ago. Giant bubbles of high-energy radiation extending above and below the Milky Way's disk hint at a more violent past. These structures may be the echoes of a time when our galaxy briefly behaved like a low-level quasar, reminding us that quasars are not exotic exceptions but a natural outcome of galaxy evolution. Quasars also play a crucial role as tools for studying the universe. As their intense light travels through space, it passes through clouds of gas and dust. These clouds leave characteristic absorption lines in the quasar spectrum, allowing astronomers to detect and analyze material that would otherwise be invisible. By studying these absorption features, scientists can map the distribution of gas in and between galaxies, measure the chemical composition of the universe at different epochs, and trace how elements heavier than hydrogen and helium were produced over cosmic time. In many ways, quasars represent the extremes of nature. They show us what happens when gravity, motion, and energy combine under the most intense conditions imaginable. They challenge our understanding of physics, push our theories to their limits, and provide clues about the earliest chapters of cosmic history. Far from being mere curiosities, quasars are central players in the grand story of the universe, linking the growth of black holes to the formation and evolution of galaxies themselves. This is only the beginning of the story. Quasars have many types, behaviors, and unanswered questions associated with them, from why some produce jets and others do not, to how supermassive black holes grew so rapidly in the early universe. To go deeper into the story of quasars, it is important to understand how such extreme objects can form so early in the history of the universe. Observations show that some quasars existed when the universe was less than 1 billion years old, yet they are powered by black holes with masses reaching billions of times that of the Sun. This creates a fundamental puzzle. Black holes grow by accreting matter, but there are physical limits to how fast this process can occur. The existence of such massive black holes so early suggests that either the initial seed black holes were already very large, or that they grew through unusually rapid or efficient accretion, possibly aided by frequent mergers in the dense, young universe. One leading idea is that the first black holes formed from the collapse of massive primordial stars, often called population 3 stars. These stars, made almost entirely of hydrogen and helium, could grow much larger than modern stars because they lacked heavier elements that would otherwise limit their size. When these enormous stars died, they may have left behind black holes hundreds of times more massive than the Sun. Over time, these black holes could merge with others and feed on surrounding gas, eventually becoming the supermassive black holes that power quasars. Another possibility is the direct collapse of massive clouds of gas into black holes, bypassing the normal star formation process altogether. This would create much larger seed black holes from the very beginning. As a quasar ignites, its environment becomes dominated by intense radiation and powerful outflows. The accretion disk around the black hole emits enormous amounts of ultraviolet and X-ray radiation, heating nearby gas and ionizing it. At the same time, strong winds can blow outward from the disk, carrying matter away at thousands of kilometers per second. These winds can have a dramatic effect on the host galaxy. By sweeping away or heating the gas that would otherwise form new stars, a quasar can effectively regulate or even shut down star formation. This process, known as feedback, is a key element in modern theories of galaxy evolution. Feedback from quasars helps explain why galaxies have the sizes and properties we observe today. Without some mechanism to limit star formation, galaxies could grow far larger and more massive than they actually are. Quasar-driven winds and radiation provide a natural way to control this growth. When the black hole becomes too active, it pushes away its own fuel supply, causing the quasar to fade. This self-regulating behavior links the mass of the black hole to the properties of its host galaxy, such as the mass and velocity of stars in a galactic bulge. Observational evidence strongly supports this connection, suggesting that black holes and galaxies grow together in an intimate cosmic partnership. Quasars come in different observational types, largely depending on how they are oriented relative to Earth and how much material surrounds their central regions. Some quasars are radio loud, producing powerful radio-emitting jets that can be detected across vast distances, while others are radio quiet, lacking strong jets or producing much weaker ones. This difference may be related to the spin of the black hole, the structure of the magnetic fields near it, or the nature of the material being accreted. In radio-loud quasars, magnetic fields may channel energy more efficiently into narrow, relativistic jets. Another important classification involves how much dust and gas obscure the central engine. In some cases, thick clouds of material block our direct view of the accretion disk and black hole, allowing us to see only certain wavelengths of light. In other cases, our line of sight is relatively clear, and we observe the full brilliance of the quasar. This has led to the development of unification models, which propose that many different types of active galactic nuclei are fundamentally the same kind of object, seen from different angles or at different stages of activity. Quasars represent the most luminous end of this broader family. The jets produced by some quasars are among the most dramatic structures in the universe. These jets consist of charged particles accelerated to nearly the speed of light and guided by intense magnetic fields. As they travel far from the black hole, they can inflate enormous lobes of radio-emitting plasma on either side of the host galaxy. These lobes can be larger than the galaxy itself, extending deep into intergalactic space. The energy carried by jets is so great that they can heat and displace gas in galaxy clusters, influencing the evolution of not just a single galaxy, but entire cosmic environments. Variability remains one of the key observational features of quasars. Changes in brightness across different wavelengths provide insights into the structure of the accretion disk and the behavior of matter under extreme gravity. By monitoring how light at various wavelengths brightens or dims over time, astronomers can infer the size, temperature, and dynamics of the emitting regions. In some cases, sudden changes in brightness may be linked to disruptions of stars that wander too close to the black hole and are torn apart by tidal forces, briefly increasing the supply of material and causing a flare of radiation. Quasars also serve as natural laboratories for testing the laws of physics. The extreme gravitational fields near supermassive black holes allow scientists to study the effects predicted by general relativity, such as gravitational redshift and the bending of light. Additionally, the high-energy environments around quasars are ideal for exploring plasma physics and magnetohydrodynamics under conditions that cannot be replicated on Earth. By comparing theoretical models with observations, researchers can refine their understanding of how matter and energy behave in the most extreme regimes. Another important role of quasars lies in their contribution to cosmic reionization. In the early universe, after the formation of the first stars and galaxies, much of the hydrogen gas between galaxies was neutral. High-energy radiation from early quasars, along with that from young stars, helped reionize this gas, making the universe transparent to ultraviolet light. While stars likely played the dominant role, quasars may have contributed significantly, especially in certain regions. Studying the distribution and properties of early quasars helps scientists understand how and when this crucial transition occurred. Despite decades of study, many questions about quasars remain open. Scientists continue to investigate why some black holes become powerful quasars while others remain relatively quiet, what determines the duration of a quasar phase, and how the earliest quasars manage to grow so quickly. New observatories and surveys, both on the ground and in space, are providing increasingly detailed data, revealing thousands of new quasars and pushing observations closer to the cosmic dawn. As research advances, quasars are increasingly seen not just as exotic anomalies, but as fundamental components of cosmic history. They illuminate the growth of structure in the universe, link the smallest and largest scales of physics, and remind us that even in the vastness of space, a single object can influence regions millions of light years across. Observing quasars is both a challenge and an opportunity for astronomers, because their extreme distances and brightness reveal information that would otherwise be inaccessible. Quasars emit radiation across nearly the entire electromagnetic spectrum, and no single telescope or instrument can capture the full picture on its own. Radio telescopes detect their jets and extended lobes. Optical telescopes record their brilliant visible light and spectral lines. Ultraviolet instruments probe the hot inner regions of accretion disks, and X-ray observatories reveal the most energetic processes occurring closest to the black hole. By combining data from all these wavelengths, scientists build a comprehensive understanding of how quasars work. One of the most important tools in quasar research is spectroscopy, the study of how light is spread out by wavelength. When astronomers analyze a quasar spectrum, they see bright emission lines produced by gas moving at tremendous speeds near the central black hole, as well as dark absorption lines caused by material lying between the quasar and Earth. The widths of the emission lines provide clues about how fast the gas is moving, which in turn allows scientists to estimate the mass of the black hole. These measurements reveal that quasar black holes range from millions to tens of billions of times the mass of the Sun. The absorption lines in quasar spectra are equally valuable. As quasar light travels through intergalactic space, it passes through clouds of gas associated with galaxies and the cosmic web. Each cloud leaves its own signature, allowing astronomers to detect and study matter that would otherwise be invisible. In this way, quasars act like backlights, illuminating the structure of the universe on the largest scales. By studying large samples of quasar spectra, researchers can map how gas is distributed across cosmic time and trace the evolution of chemical elements from the early universe to the present day. Gravitational lensing adds another layer of insight into quasar observations. When a massive object, such as a galaxy or galaxy cluster, lies between a quasar and Earth, its gravity can bend and magnify the quasar's light. This can produce multiple images of the same quasar, arcs of light, or even complete rings. These lensing effects not only make distant quasars easier to observe, but also provide powerful tools for studying the distribution of dark matter in the lensing objects. In some cases, tiny variations in the brightness of lensed quasar images reveal the presence of stars or smaller structures within the lensing galaxy. Time-domain astronomy has become increasingly important in quasar studies. By monitoring quasars over long periods, astronomers can observe how their brightness and spectra change. These variations can be caused by instabilities in the accretion disk, changes in the flow of material, or interactions between the disk and the black hole's magnetic fields. In lensed quasars, time delays between brightness changes in different images allow scientists to measure cosmic distances and even estimate the expansion rate of the universe. Quasars also provide clues about the geometry and structure of matter near supermassive black holes. Reverberation mapping is a technique that uses time delays between changes in the quasar's central light source and the response of surrounding gas clouds. By measuring these delays, astronomers can estimate the size and structure of regions that are far too small to be resolved directly by telescopes. This method has been instrumental in refining black hole mass estimates and improving our understanding of how accretion disks and surrounding gas behave. As observational technology has improved, surveys have discovered vast numbers of quasars. Early studies identified only a few dozen, but modern sky surveys have cataloged hundreds of thousands. These large data sets allow astronomers to study quasars statistically, revealing patterns in their distribution, luminosity, and evolution. One key finding is that quasars were far more common in the early universe than they are today. Their numbers peaked when the universe was only a few billion years old and have declined since then, reflecting changes in the availability of gas and the growth of large-scale cosmic structures. Quasars are also important markers of large-scale structure. Because they are so luminous, they can be observed at great distances, making them excellent tracers of the cosmic web. Studies of quasar clustering show that they tend to reside in massive dark matter halos, often in regions where galaxies are forming and interacting. This supports the idea that galaxy mergers and interactions play a significant role in triggering quasar activity by funneling gas towards central black holes. The study of quasars has benefited greatly from space-based observatories. Earth's atmosphere absorbs much of the ultraviolet and X-ray radiation emitted by quasars, making space telescopes essential for a complete view. Observatories operating in these wavelengths have revealed hot coronae of energetic particles, near accretion disks, rapid X-ray variability, and signatures of winds and outflows moving at relativistic speeds. These observations have helped confirm theoretical models of how matter behaves in the strongest gravitational fields known. Looking ahead, the future of quasar research promises even deeper insights. New generations of telescopes will detect fainter and more distant quasars, pushing observations closer to the era of the first black holes. High-resolution instruments will allow astronomers to study the environments of quasars in greater detail, revealing how they interact with their host galaxies and surrounding intergalactic medium. Advances in computing and simulation will also play a crucial role, enabling more realistic models of accretion, jets, and feedback. Through these ongoing efforts, quasars continue to serve as both beacons and laboratories. They illuminate the distant universe, probe fundamental physics, and connect the smallest scales of black hole horizons to the largest scales of cosmic structure. The broader impact of quasars on the universe becomes clear when they're viewed not as isolated objects, but as powerful agents of change acting over immense distances and long periods of time. One of their most significant influences is on the gas that fills and surrounds galaxies. When a quasar is active, its intense radiation and fast-moving winds can heat, ionize, and expel vast amounts of gas from the central regions of its host galaxy. This process alters the future of the galaxy by determining how much raw material remains available for forming new stars. In some cases, quasar activity appears to shut down star formation almost entirely, transforming once vibrant, star-forming galaxies into quieter, more passive systems. At the same time, quasar influence is not always purely destructive. Under certain conditions, the compression of gas caused by quasar-driven shocks can actually trigger bursts of star formation in surrounding regions. This dual role highlights the complexity of quasar feedback. Rather than acting as simple on-off switches for star formation, quasars participate in a dynamic interplay of heating, cooling, compression, and expansion that shapes galaxies in diverse ways. Understanding this balance is one of the central challenges in modern astrophysics. Beyond individual galaxies, quasars affect the intergalactic medium, the vast reservoir of gas that lies between galaxies. Powerful jets and radiation from quasars can travel far beyond their host galaxies, depositing energy into this diffuse material. This heating can prevent gas from cooling and collapsing into new galaxies, influencing the growth of structure on the largest scales. In galaxy clusters, quasar-related activity is thought to help regulate the temperature of hot gas, preventing it from cooling too quickly and forming stars at rates that would conflict with observations. Quasars also leave lasting imprints on the chemical evolution of the universe. The winds and outflows driven by quasar activity can carry heavy elements, forged in stars, out of galaxies and into intergalactic space. Over time, this process enriches the universe with elements beyond hydrogen and helium, spreading the building blocks of planets, life, and complex chemistry across vast regions. Observations of distant gas clouds enriched with metals provide evidence that quasar-driven outflows played an important role in distributing these elements early in cosmic history. Another profound contribution of quasars lies in their connection to the growth of supermassive black holes. By studying quasars across different epochs, astronomers can trace how black holes gained most of their mass. Evidence suggests that a significant fraction of black hole growth occurred during luminous quasar phases, when accretion rates were high and energy output was intense. This means that the brilliant light we observe from quasars is not just a byproduct of black hole growth, but a key record of how these massive objects assembled over time. The relationship between quasars and galaxy mergers is particularly important in this context. When galaxies collide or interact, gravitational forces can drive large amounts of gas toward their centers. This influx of material can ignite both intense star formation and quasar activity. Observations of quasar-host galaxies often reveal signs of past mergers, such as distorted shapes, tidal tails, or multiple nuclei. These findings support the idea that major galactic interactions are a common trigger for the most luminous quasar phases. Quasars also challenge and refine our understanding of fundamental physics. The extreme environments near supermassive black holes provide natural laboratories for testing theories of gravity, magnetism, and high-energy particle acceleration. The behavior of matter under such conditions pushes current models to their limits, revealing where refinements or entirely new theories may be needed. For example, studying the structure and variability of quasar accretion disks helps constrain how angular momentum is transported and how energy is dissipated in turbulent plasmas. On cosmological scales, quasars serve as valuable probes of the universe's expansion and large-scale structure. Their brightness allows them to be observed across vast distances, making them useful markers for tracing the distribution of matter over time. Measurements involving quasar clustering, absorption features, and gravitational lensing contribute to our understanding of dark matter, dark energy, and the overall geometry of the cosmos. In some studies, quasars have even been used to test whether fundamental physical constants have remained unchanged over billions of years. As scientists push observations to ever higher redshifts, quasars provide glimpses into the era when the first galaxies and black holes were forming. These early quasars illuminate a time when the universe was undergoing rapid transformation, transitioning from a relatively simple state to one filled with complex structures. By studying them, astronomers gain insight into how quickly order emerged from the aftermath of the Big Bang and how the seeds of today's galaxies were planted. Despite the progress made so far, quasars remain sources of deep mystery. Questions persist about the exact mechanisms that launch and collimate their jets, the detailed structure of their innermost regions, and the reasons behind the enormous diversity in their observed properties. Some quasars appear to flicker on and off over cosmic timescales, while others shine steadily for millions of years. Determining what controls these behaviors is an active area of research. As the study of quasars moves forward, it increasingly focuses on the unanswered questions that lie at the edges of current knowledge. One of the most pressing mysteries concerns the earliest quasars in the universe. Observations have revealed quasars that existed when the universe was only a few 100 million years old, already powered by black holes billions of times more massive than the Sun, explaining how such enormous black holes formed and grew so quickly remains a major challenge. Competing ideas include rapid, sustained accretion at rates near or above theoretical limits, the formation of unusually massive seed black holes through direct gas collapse, and frequent mergers in dense early environments. Each possibility has different implications for how structure formed in the young universe. Another open question involves the detailed physics of accretion disks. While the general picture of matter spiraling into a black hole is well established, the fine-scale processes that govern how angular momentum is transported and how energy is released are still not fully understood. Turbulence driven by magnetic fields is thought to play a key role, but modeling these processes accurately is extremely difficult. Quasars, with their immense luminosities and variability, offer some of the best opportunities to test and refine these models, linking theoretical predictions with observational evidence. The origin and behavior of quasar jets also remain areas of intense study. Not all quasars produce powerful jets, and among those that do, the properties of the jets can vary dramatically. Understanding why jets form in some systems and not others may depend on factors such as black hole spin, magnetic field configuration, and the nature of the accreting material. Jets transport enormous amounts of energy far from the black hole, making them key drivers of feedback on galactic and intergalactic scales. Unraveling their formation and evolution is essential for a complete picture of quasar impact. Time variability adds another layer of complexity. Some quasars appear to turn on and off over relatively short cosmic timescales, suggesting that quasar activity may be episodic rather than continuous. These changing-look quasars challenge traditional classifications and indicate that the structure of the central regions can evolve rapidly. Studying such transitions provides valuable insights into how accretion flows respond to changes in fuel supply and environmental conditions. Future observatories promise to revolutionize quasar research. New telescopes with greater sensitivity and resolution will detect fainter and more distant quasars, pushing observations closer to the formation of the first black holes. Improved instruments across the electromagnetic spectrum will allow astronomers to probe quasar environments in unprecedented detail, from the innermost regions near the event horizon to the large-scale effects of outflows and jets. These observations will help answer long-standing questions about how quasars interact with their surroundings and how they influence cosmic evolution. Advances in computational power are equally important. High-resolution simulations that combine gravity, magnetism, radiation, and fluid dynamics are becoming increasingly realistic. By comparing these simulations with observations, scientists can test competing theories and refine their understanding of the physical processes at work. This synergy between observation and theory is crucial for making progress in a field as complex as quasar astrophysics. Quasars also continue to play a role in broader cosmological studies. Their distribution and properties provide constraints on models of dark matter and dark energy, while their absorption spectra reveal the structure and composition of the intergalactic medium. As datasets grow larger and more precise, quasars will remain valuable tools for probing the fundamental parameters that govern the universe. In a broader sense, quasars embody the interconnected nature of cosmic evolution. They link the smallest scales, where gravity dominates near black hole horizons, to the largest scales, where galaxies and clusters shape the cosmic web. Their light carries information across billions of years, allowing us to reconstruct the history of matter, energy, and structure from the early universe to the present day. Ultimately, quasars remind us that the universe is capable of producing phenomena far beyond everyday experience. They are not just distant curiosities, but key actors in the grand narrative of cosmic history. By studying quasars, we gain insight into how galaxies form and evolve, how black holes grow, and how the universe itself changes over time. Even after decades of research, quasars continue to surprise and inspire, standing as some of the most extraordinary engines of light and power ever discovered.